Welcome to Lecture B16. In this lecture, we'll talk about distributions of several random variables. And let's jump right into this by working a problem. This will be problem 24.9.2. We're asked to do the following. It says, find the probability that x is greater than 4 and y is greater than 4 and the probability that x is less than or equal to 1 and y is less than or equal to 1 if the pair of random variables x, y has the density little f of x, y is equal to 1/32 if x is greater than or equal to 0, y is greater than or equal to 0, and x plus y is less than or equal to 8. Okay, so the first thing I would do in trying to understand this problem better, well, actually, to be honest, the first thing I would do is to read section 24.9 in the book. But then after reading that section, if you're trying to tackle this problem, then the first thing that I would do is to graph the region in the XY plane under consideration. So what we have then in this case is the following. Here is x and here is y. And we see that we're interested in x greater than or equal to 0. So that means we're interested in the half plane to the right of and including the y-axis. And we're also interested in y greater than or equal to 0. So this is the half plane above and including the x-axis. So now we're just talking about this upper right-hand quadrant number 1, including the axes. And then we also want to only consider x's and y's that satisfy the relationship that x plus y is less than or equal to 8. Now, if you think about that for a moment, let me put some numbers here on these axes. We'll say 0, 2, 4, 6, and 8, and likewise here 0, 2, 4, 6, and 8. And if you think about it for just a moment, the region that is being discussed here is the following. It is the triangular region shown here. This is the region in which x would be greater than or equal to 0, y would be greater than or equal to 0, and x plus y would be less than or equal to 8. Now, the first thing I want to point out to you and that it's not really necessary to make this observation in order to do this problem, but it will be a nice thing to know for some of your future problems. So I'll just make this observation. I'll say observe that the integral from negative infinity to infinity of little f of x, y, and actually this is a double integral now, well, remember that little f of x and y is equal to 1/32 inside this triangle, and it's equal to 0 everywhere else. So this would be equal to integral negative infinity to infinity. Well, let me rewrite it like this. Of course, when we integrate 0, we get 0. So we only have to worry about the part over the triangle. So I'll just say triangle, and I won't try to fix the boundaries. 1/32 dx dy, and so we get the 1/32, of course, is a constant, so it can come outside of the integral. So we get 1/32 times the integral over the triangle of dx dy, and the integral of dx dy over a triangle is just the area of the triangle, so we get 1/32 times the area of the triangle, and the area of a triangle is 1/2 the base times the height, so we get 1/32 times 1/2 times the base, which is 8, times the height, which is 8, and so we get 64. 8 times 8 is 64 over 2 times 32, which is 64, and we get 1, which is just like we had before when we're looking at single random variables. When we integrate the density function over all possible values, we must get 1, and the same is true here for this pair of random variables, x and y. When we integrate the density function for the pair, then we get 1, just as we did before for one random variable. So that, again, that's just an observation. It's not something you necessarily need to do in order to solve this problem, because remember, what we're actually asked for here is the probability that x is greater than 4 and y is greater than 4. That's one thing we need to find, and then the other thing we need to find is probability that x is less than or equal to y and y is less than or equal to y. So to find those, we really didn't have to do this calculation, but it's a nice thing to observe. Okay, so how do we get these problems that we want to solve? The probability that x is greater than 4 and y is greater than 4. Okay. Now the probability that x and y are greater than 4 is I'm afraid that my graph is not great here, but this would be the point 4, 4. It actually lies on this line. And so the probability that x and y are both greater than 4 is actually 0, because the region that we're talking about here, let's think about it. The probability that y is greater than 4 is everything above this dashed line, everything above that, and the probability that x is greater than 4 is everything to the right of this dashed line. And so the probability that x is greater than 4 and y is greater than 4 Well, we're talking about this region. I'll put dots in it. We're talking about this region out here, but everywhere in that region, little f is equal to 0. So if we integrate little f over that entire region, even though it is an infinite region, if we integrate little f over that entire region in order to find the probability here, we get 0. Now so that part of this problem is easy. Now let's look at the second part, the probability that x is less than or equal to 1 and y is less than or equal to 1. Now this is a more interesting problem. That, of course, the probability that y is less than or equal to 1 means that we're looking at everything below this dashed line, and the probability that x is less than or equal, and actually it shouldn't be dashed now because we're looking at less than or equal to. So probability for y is less than or equal to 1, we have a solid line there. For x less than or equal to 1, we have a solid line here. And the region that satisfies both of those, I'll just make it solid, is this region. Now actually it includes this region as well out here, but we don't need to worry about that because f of xy is equal to 0 out there. So the only part that we have to worry about is this part here that's colored solid, and so we have integral from 0 to 1, integral 0 to 1 of 1/32 dx dy, and that's 1/32 times the integral from 0 to 1, integral 0 to 1 dx dy, which is 1/32 times 1 times 1, and that will just give 1/32. So the probability that x is less than or equal to 1 and y is less than or equal to 1 is simply 1/32. And that's how we would do problem number 2. Now let's look at problem number 3, which is slightly more complicated. Okay, so this is P 24.9.3. Actually, let me go ahead and 24.9.4 is directly related to our problem we just did. So let's do it first, and then we'll come back to 3. Okay, so 24.9.4 asks the following: find the density of the marginal distribution of x in problem 24.9.2, the one that we just did. Okay, so using the notation that your book uses for this, we'll have f sub 2 of y, and what we will need to do is come back up to our picture for problem 2, which is right here, and let's just repeat that picture because it got a little busy there, so let's repeat it here. So here's x and y, and 0, 2, 4, 6, 8. Okay, so here again is a reminder that remember that little f of xy is equal to 1/32 inside this triangle and 0 everywhere else. Now, how do we find this marginal distribution of x? Well, we choose an arbitrary x. We don't want to make it a particular value, just some arbitrary x that can be anything here between 0 and 8. In fact, well, anything outside of 0 or 8, the marginal distribution is going to be 0. But if we choose an x between 0 and 8, then to find the marginal distribution, we will choose that x and then let y vary over all possible values. And so what we get here is the integral of f. We want to integrate f of xy. And as I said, we're letting y vary, so dy. And for the obviously, so let's say that this is the x that we've chosen, some arbitrary x here. So the minimum, the lower limit on this integral is the lowest value for y is going to be 0. But what is the upper value for y? Well, remember that this line here, the hypotenuse of the triangle, is the line x plus y is equal to 8. Or in other words, y is equal to 8 minus x. So that's the upper limit. Notice we're just integrating from, we've picked our arbitrary x, and now we're going from the least possible y, which is 0, to the greatest possible y, which is 8 minus x. And notice that that depends on x. Obviously, if we chose an x over here, the greatest y would be larger. If we chose an x over here, the greatest y would be smaller. So this upper limit depends on x, and that's clearly shown from the formula, because we have, as I said, 0 for the lower limit. That, of course, does not depend on x, but the upper limit of 8 minus x does clearly depend on x. And now inside that region, f of xy is 1/32, so we get f2 of y is integral from 0 to 8 minus x of 1/32 dy. The 1/32 is a that term is a constant, so it can come out. And we have integral from 0 to 8 minus x of dy, and that's just 8 minus x, and so we get 8 minus x over 32. And that would be the density of the marginal distribution of x in problem 2. Okay, now let's look at still another problem. This was problem 24.9.6. And pay especially close attention to this one, because both of your homework problems will be closely related to this problem. So it says, if certain sheets of wrapping paper have a mean weight of 10 grams each, with a standard deviation of 0.05 grams, what are the mean weight and standard deviation of a pack of 10,000 sheets? And again, now both of the problems at the end of this lecture are going to be closely related to this problem, so pay careful attention. It's actually very easy once you see the trick. Okay. Well, as the book explains, the mean of the sum of random variables is the sum of the means, and so for each sheet of wrapping paper has a mean of 10 grams, and there are 10,000 of these, and therefore the mean for the 10,000 is just 10,000 times 10 grams. So we get 100,000 grams as the mean. Now, what about the standard deviation? Well, the way that we calculate this is the following. The means, if you have a sum of random variables, the means add together, and so do the variances. Now, it's important to note the standard deviations do not add. It's not the standard deviations that add, it is the variances that add. And so, therefore, in order for us to find the standard deviation for the entire pack, we have to add up the variances for all the sheets. Now, what is the variance for an individual sheet? Okay, sigma squared for an individual sheet that will be, since the standard deviation is 0.05 grams, then we have to square that to get the variance. And so we get 0.0025 grams squared. That's sigma squared for an individual sheet. So, now that's the variance, and the variances do add. So, sigma squared for the entire pack is equal to 10,000 times 0.0025 grams squared, and that would be equal to 25 grams squared. And so now the standard deviation, so sigma for the entire pack, well, that will be the square root of sigma squared for the entire pack, which is the square root of 25 grams squared, which is 5 grams. Sigma for the entire pack is 5 grams. And that's how you find the mean for a sum of random variables and the standard deviation for a sum of random variables. So it's actually quite straightforward. Look at a couple of problems for this lecture. Okay, so as was mentioned, both of the problems here at the end of the lecture will be similar to problem 6 that we just did. And then the other problem that we'll do in class, you should be ready for something more similar to problems 2 and 4, particularly problem 2. Okay, so let's look at these problems now, the ones that are similar to problem 6. Both of the problems, both B16-1 and B16-2, refer to this situation, which is the same as the situation described in problem 24.9.7 of your text. It says certain transformer cores consist of 50 layers of sheet metal and 49 insulating paper layers. The metal sheets have mean thickness of 0.55 millimeters each, with a standard deviation of 0.05 millimeters, and the paper layers have mean thickness 0.05 millimeters each, with a standard deviation of 0.02 millimeters. And let me emphasize that's not a 6.2 there, that's 0.02. Okay, so with that information given, question B16-1 is, what is the mean thickness of a transformer core? And the choices are A, 27.45 millimeters, B, 25 millimeters, C, 2.45 millimeters, and D, 0.55 millimeters. And then question B16-2, what is the standard deviation of the thickness of a transformer core? Choice A is 3.48 millimeters. Choice B is 0.38 millimeters, choice C is 2.5 millimeters, and choice D is 0.98 millimeters. So those are the two lecture problems. Again, they're both similar to problem 6 that we did in the lecture. And then expect at least one more problem in class, and particularly look at particularly review problem 2 here to prepare for that. And so that concludes lecture B16, and good luck.